So, good afternoon, everyone. My name is Simrat Pal Singh, and my teammates Apurva and Raghvendra Salian. We are here to present a paper, Room Temperature Entanglement Between Single Defect Spins in Diamond. So, starting with the background, entanglement generation between photons has been showed in various um, papers and developments, but uh, entanglement generation between solid state spin qubits has been one of the remarkable developments in the field. So one way to generate entanglement here, our task is to show how we can generate entanglement using NV spin defects. So let's start with how NV centers are created. To start with NV centers, let's take a carbon 12 enriched diamond, and to create a NV defect in the diamond, we can make use of a 20 nanometer mica mask of depth 10 micrometers and holes of the diameter 20 nanometers. These holes can be kept at a distance of 25 nanometers apart, and we can then implant nitrogen 15 ions onto this mica sheet, and they can be implanted at a distance of around 20 to 25 nanometer apart. Uh, Once that is done, we carry out annealing at a temperature of 800 to 1000 degrees Celsius. With a success rate of 2%, we get NV centers in carbon 12 enriched diamonds. Why we take carbon 12 enriched diamonds instead of carbon 13? Because carbon 13 can produce stray magnetic fields that can hinder the coherence time of the NV defect centers. So let's move on to what happens once we have created an NV defect center, what happens at the spin level interaction. So to start with, NV ground center, ground level state, they have a triplet state. That is, the total spin is equals to 1, which gives us three sub spin levels, ms equals to 0, +1, and -1. If we take a look at here at the Hamiltonian, we have three terms here. The first one corresponding to a zero field splitting. That means when we have created an NV center, we have a singlet triplet spin state. Corresponding to that, we have three sublevels. A zero field splitting, what it does is it creates a splitting between those sublevels. M is equal to 0 and M equals to -+1. After that, if we apply a magnetic field across this NV defect center, the +-1 sublevels, they also split further due to Zeeman splitting. And the last here is the one that we need to consider here right now. That is, if we take two NV centers that are placed very adjacent to each other in a diamond, as we discussed earlier, they were 25 nanometers apart. If we want to use them to generate an entanglement, we need to create a coupling between them. That coupling can be generated using their magnetic dipole moments. And this term in the Hamiltonian, this corresponds to the coupling between the two electronic spin states of the adjacent NV centers. So moving on forward, the term here, nu dip, it corresponds to coupling constant of the dipole moments between the two electron spin states of the NV centers. Normally what happens is we have a transition between ms is equals to 0 and m equals to 1. We call it a single quantum transition. When a single quantum transition occurs in either of the NV centers, the coupling constant has a value of around 4.93 kilohertz. And to attain a strong coupling between two NV centers, we need to have this value more than the defacing time, that is the T2 star value of the NV centers. But since we have factors like stray magnetic fields or paramagnetic impurities, these lead to inhomogeneous broadening, what we call as spectral diffusion of the spectral lines. And that's why even after refocusing of using a spin echo sequence, we cannot get the coupling constant higher than the decoherence rate. So what we do is we switch to double quantum transitions instead of single quantum transitions. So what happens here is instead of going from ms equals to 0 to plus minus 1, we choose to go from ms equals to 1 to minus 1. We now work with ms equals to 1 and minus 1 and discard ms equal to 0 for the time being. So when we do that, we notice that the value of this coupling constant has been increased by a factor of 4. Why this happens is, since we are now working with delta ms is equals to plus minus 2, the phase evolution is now twice its previous factor. It's evolving at double the rate it was earlier. And since it's delta ms equals to plus minus 2, the change in magnetic field is also double as compared to the previous. So two double factors lead to a fourfold, let's say fourfold times the previous value of the coupling constant when we had single quantum transitions. Now so yes, since now we have moved to double quantum transitions, still we have one problem, that is still this coupling constant is lower than the decoherence rate of the NV center electronic spin states. So what we can do is, here we can see the dephasing time is around 27 microseconds and 22 microseconds for both of the NV centers. What we can do here is now we can apply the technique of refocusing the spins that will nullify any noise, local noise that has been introduced to the spin level due to stray magnetic fields or paramagnetic impurities. That can be done using spin echo sequence, and this leads to increase of the dephasing time to a total coherence time of 150 microseconds and 540 microseconds. So when this is done, we'll notice that since T2 value has increased from T2 star, the inverse of T2 will reduce and corresponding value of our coupling constant will increase. Next, we have created a coupling between two different NV centers, but how to generate an entanglement between them? So that can be done. Let's say we start with both the NV centers initialized in the 0, 0 state. They are both not entangled right now. These all refer to the mixed states. They are what we say separable states, product states. So starting with both the NV centers in the 0, 0 spin state, we apply pi by 2 poles that puts both of these in a superposition of +1 and -1, the two states that we are working with right now. Then we leave both the states. Okay, sorry, it had to go. Okay, so we start with this state, that is 0, 0 state, and this corresponds to this point at in the circuit. So starting with 0, 0 state, we then apply a pi by 2 poles that puts each of these. First 0 represents the state of the first NV center. Second 0 represents the state of the second NV center. When we apply a pi pulse, both of these are put in a superposition of +1 and -1, and we get a product state corresponding to this. Here all are okay. So after that, we leave that system for phase evolution under the coupling that we have of the two NV centers. So during this coupling, the NV center, the two states that have the same product signs, they require a phase over this time due to the coupling between the NV centers. The next step would be applying a pi pulse. Okay, so that was the previous one. Applying a pi pulse that again accounts for all the local noise that has been introduced in the spin states. This will be followed by another free evolution of the system, and then we apply at the end another pi by 2 pulse that projects the whole system into an entangled state, this entangled state. Here you can see we have a factor of phi that represents the phase that has been accumulated over the time during free evolution of the system. If we want to have a maximally entangled state of this, we can tune the values of this phase that has been accumulated, and that can be done through here. If we keep the phase value equal to this quantity, and at the end we get the free evolution time equals to 12.5 microseconds, this will lead to a generation of a maximally entangled state. Now the maximally entangled state is between -1 and +1. So what if we want to read this state, we want to measure the state. Since in NV centers, the readout is done through fluorescence, and that is dependent on the sublevels, +1, -1, and 0. And the maximum intensity that we obtain is corresponding to ms equal to 0. And we can't get it here because it's +1 and -1. So what we do is we somehow try to convert this maximally entangled state into another basis that consists of the 0 states. That can be done using 2 pi pulses. 2 sequential pi pulses will transfer this entangled state onto one of the Bell states. Okay, so now to measure, once we have achieved an entangled state, the next task is to measure the entanglement or to quantify the entanglement. That can be done using quantum state tomography. So our density matrix was reconstructed using quantum state tomography, and a 0.67 approximately fidelity was obtained with respect to the initial state that had been like target state. Also, now once we have, let's say we created a Bell state here. Now if we want to measure whether this is entangled or not without using quantum state tomography, we can make use of fluorescence, but the fluorescence that corresponds to a psi state, a phi state, and a product state, not an entangled state, the intensities will be identical for a product state and a mixed state and an entangled state. So to differentiate between these two, what we do is we carry out photon correlation measurements. In photon correlation measurements, what we want to check is if two photons from two different sources are coming at the same point, at the same time. So since we have now, suppose we have 3 different types of states, a state phi, a state psi, and a mixed state, that is not entangled state. This state phi, it corresponds to bunching of photons because as you can see here, both of the NV centers are in the same state at the same time. It's opposite for the psi state. It goes as 0, 1 plus 1, 0. So phi corresponds to bunching of photons, whereas psi corresponds to anti-bunching of photons. While the mixed state that we have, the product state we have, it is very unlikely. It is a 50-50% chance that we can get a photon, 2 photons at the same time or not. So that's why the probability of getting 2 photons will be higher for phi than the mixed state, and it will be lower for psi than the mixed state. And thus, carrying out quantum photon correlations, we can check if a state is entangled or not. Then we have the fidelity of the, I've already discussed that result. We also carried out von Neumann entropy. So von Neumann entropy is a measure to quantify entanglement between 2 states, where 0 corresponds to no entanglement and 0.69 corresponds to complete entanglement, maximally entangled states. So lifetime of these entangled states, the phi plus that we had discussed earlier that we had obtained at the end, the Bell state, is 28 microseconds. And if we had applied some other operation and obtained psi plus instead of phi plus, we would have obtained a lifetime of 24 microseconds. But these states are now limited by the defacing time of the electron spin. So what shall be done to preserve this entanglement? If we are coming across defacing, that will just take away our entangled state. So that can be done using entanglement storage. Entanglement storage means that we want to map our state, our part of our entangled state. So our entangled state will have 2 parts. We are like, just take one part, and we want to map the state to somewhere else where it has a higher coherence time, lesser defacing, so that can be stayed for a longer time. That can be done if we work with nuclear spins instead of electronic spins. So what we do is, once the entanglement is generated, we carry out a non-aligned magnetic field that will couple the NV center's electronic spin with the nuclear spin. Once that is done, we carry out selective pi pulses, controlled pi pulses that will map the entangled state from the electronic spin states to the magnetic states. And that is how entanglement can be stored in spin states, and it will stay there until we retrieve it ourselves, or it can be lost after around 7.5 milliseconds. So it's a very high time. This is one of the results of storage. So the blue line here represents the reference that was not stored, the fidelity of the amplitude of the photon that was not stored, and the orange is the retrieved photon from the NV center. So you can see here a peak in the stored photon as well that like clarifies or that confirms that upon storage also the coupling between the two NV centers, the entanglement is preserved. So this is the result of entanglement storage. Here we can see this is the lifetime of the states without storage, and this corresponds to the lifetime of the entangled states when we use storage in nuclear spins. That's all. Thank you.
I have one question. In the entanglement state that you showed there, so when you are setting up the double quantum condition there by setting the t equal to mu d t something, so you are supposed to get some pure state out of it because your scaling factor has e to the power minus 2p plus 1.
I didn't get it.
And
Please again.
if you can refer to your slide there.
Sorry.
Maybe you can come
Okay,
closer
sir.
to.
Uh,
So where you first showed the entanglement states, the psi.
okay, so
Uh, yes, this one. So here you have shown that your basis 1 1, it has the coefficient of e to the power minus q I phi plus 1. But you already, when you are setting up the double quantum condition above, you have written e to the power minus q I phi plus minus 1.
no, that is not done before.
That is done before.
No, that's not done before, and that's something. That is a condition that we want to imply when we want to have a maximally entangled state here.
Okay.
So we put the value of e to I phi such that it becomes minus 1,
Uh-huh.
so that the output here we have an entangled state, maximally entangled state.
So you are also putting that for the coefficient of the basis state 1 1
Where? Here?
in the psi phi
Psi
for the
5.
basis state 1 1. Yes.
So yes, that's where we're putting the value of e to power I phi.
So you are putting minus 1 there. So minus 1, minus 1, minus 2, something like that, because we are getting also 1 by root over 2 for phi of
Oh,
the.
okay, so this might be a mistake here. It should be minus 1 here.
And this is actually should be the mixed state to pure state. You are supposed to get only the pure state for this.
How?
I mean that minus 1 plus 1 would be 0 now for basis state 1 1.
Okay, so this has to be minus 1 actually. Minus 1, minus 1.
Okay. And also there one other question that how are we getting to selectively getting to the double quantum transfer?
Double
Like
con.
we are saying that we are transferring from minus 1 to plus 1 or plus 1 to minus 1.
So when we have a two-level system, let's say the system is initialized in the 0 state,
Mm-hmm.
we apply a pi by 2 pulse, and that puts the system in a superposition state of 0 and 1.
Yes.
But when we have a qubit system, three-level system, and you have initialized in a 0 state, and when you apply a pi by 2 pulse to that, it will put that state into superposition of the remaining two states, not the first that was initialized into. So if you have initialized in 0 and you are putting a pi by 2 pulse on that, the resulting will be a superposition state of plus 1 and minus 1.
But you should also be Hamiltonian term. But I guess that we are supposed to have some double quantum terms that will transfer between the two states.
If
You
in
are
the
only
interest of time, let me interrupt. So maybe you can have a discussion
okay.
over a tea. And so
Okay.